So welcome to this learning session on understanding process capability. This topic is very much part of I would say it's an important area for the current state of measurement within the any Lean Six Sigma project, that is the measure phase. So this topic becomes relevant when you want to measure the current state of any process performance, be it in a manufacturing industry or be it in a service industry or in your day-to-day life. So within the DMAC process. So at the end of this session, you will learn how to appreciate the necessity of process capability and what is it all about. You also learn how to measure the baseline performance using short-term and long-term capabilities of a process. Baseline performance is necessary as a start point for improvement because it's always with reference to the expectation. You can also measure the result of your improvement efforts. You will learn computing capability indices and interpreting the result with respect to your prognosis on whether you can meet the customer's specifications or fulfillment. It will give you a certain assurance to your existing capabilities. You can solve real world problems for both variable as well as attribute data, as I said, both in the service industry as well as in the manufacturing industry. In this session, you will learn about the formulae, about the computations, both manually as well as including Microsoft Excel and Minitab. I'll just spend some time in telling you it's a very easy thing. All this comes to you from a Lean Six Sigma practitioner who spent about 23 years in corporate life in senior management position with some of the world-class companies and went on to pursue his second career as a teacher, trainer, and a consultant. In operational excellence, facilitating Lean Six Sigma projects in client organizations and in supply chain operations. And that is me, V. Ashok Kumar. Welcome you to this session. Now let us deep dive into the topic straight away. So you have been introduced to two terms, voice of the process and the voice of the customer, called as VOP and VOC. Now capability is something which is a kind of analysis to provide a quantitative assessment of the ability of your process to meet the requirements. That is the voice of the customer. Now, to make it clear, let me use two real-world examples. One from the healthcare industry, where a hospital wanted to ensure patients were admitted within a particular time frame from the emergency waiting room. So they used a lot of historical data and some tools like control charts, capability indices to measure the current state of the process. And eventually they found that it was not capable. It frequently exceeded the 30-minute standard, especially during peak periods. So they had to work on a Lean Six Sigma project to bring this within 30 minutes. That is basically to do with shortening the cycle time. Let us take another example from the manufacturing industry, where an automotive manufacturer produces a part which is to a tight dimensional tolerance, let us say about 50.2 mm to 49.8 mm, where about 40.40 mm tolerance is there. And very often they found that it resulted in customer complaints and process scrap. So studies revealed that the current process capability level was not within these tolerances. It exceeded the limit given by the customer, basically due to the root cause of tool wear. That is, it's in the case of a milling machine where the milling cutter wears out with usages and the variation on the part increases. So there is a particular frequency in which the cutting tool has to be replaced. to see that the variation is within the specification limits. This is basically to do with inconsistent output. I hope you understood. As we go along, we can learn, you will have a better understanding. Now, so to put it in a nutshell, when you say the capability of a process, it has two elements in it. One is the spread, the other is the center, off target. You call it as off target. Now, let me give an example of this. Think of aircraft on a runway. While the pilot may be efficient to land the aircraft within the runway, within the particular width of the runway, he must ensure that he is always at the center of the runway. You know, there's a line marked, and he ensures that his aircraft wheels go on the center line, so that he doesn't risk he doesn't have a risk of swerving the aircraft away from the center line, either to the left or to the right. So if you think that the process of landing an aircraft in a runway should be capable, then there are two things. One is he has to reduce the spread without swerving too much, and also he has to ensure that the wheels are always towards on the center line, so that whatever little mistake he makes is within the width of the runway. And this happens in many processes. We will have a better understanding with some more examples as we go along. So that brings us to the definition of process capability in a statistical language, I would say. It is a measurement of how the process is performing with respect to a desired outcome. So go back to the voice of the customer and the voice of the process, which is determined by the customer. The voice of the customer is determined by the voice of the by the customer. So he says how much variation is allowed, and you are as a supplier, you are measuring the voice of the process, which is determined by the inherent capability of the process. So that brings us to a formula called allowed variation divided by actual variation, which is nothing but a mirror of VOC and VOP. So put this in a statistical term with a normal curve. Let us accept that the process forms a normal curve, and let us talk about Six Sigma limits, that is 6S. So we want the process to be within the Six Sigma limits. That means we have a good quality process where we produce less rejects. So this means that the normal curve should be within the Six Sigma limits. The process variation must be within the Six Sigma limits, so that we don't have the risk of producing a reject. That is in the first picture, you can see that. VOP, voice of the process, that is the upper specification limit minus the lower specification limit, is within the Six Sigma limits. That is 3 sigma on either side from the mean, that is the target. Now, take the second picture. The first picture is of a good capability process. The second picture is of a poor capability process, where the difference between the upper control limit and the lower control limit is the Six Sigma band is far wider than the wider than the specification tolerances given by the customer. So we run the risk of producing reject products whenever our process overshoots the either of the specification limits. So that brings us to saying that the voice of the process should always be lesser than the voice of the customer. In other words, the band in which the process works should be, that is the Six Sigma limits, should be less than the specification what is allowed by the customer. So the voice of the process must be within the specification limits, so that we don't run even the smallest probability of producing a bad product or making an error. I hope that's clear. Any questions you can ask, you can put it in the chat box. Now, let me sum up what we said so far, saying that the process capability is nothing but the inherent ability of a process to meet specification of the customer without any additional efforts, in the sense that whatever normal process we adopt in our operations should be enough to meet the capability rather than taking any special efforts. I recall the time when 30 years before we used to produce products for our overseas customers. Now, whenever the process was not capable, we used to take extra effort, double the time, to put more people, to put a extra good machine, to see that the lot we produce to the customer is always of the best quality. But if we take such additional efforts, then what happens is we cannot be efficient and we cannot be productive in the normal way we are working. So when I say additional efforts, the process capability means that it does not use any, the process does not use any additional efforts like time, money, manpower, technology, and typically manipulation. No, you can put an extra inspection to see that you don't make a mistake. But extra inspection involves both manpower and time, increasing your cost of the product. So the process capability helps us to see whether the process is at the center, which means whether the average measurements is very close to the mean. Then the variation, we talked about the variation should be, the spread should be less than the specification limits. Or sometimes the process can be a combination of both. That we will see a little later. So we have to ensure that these two variables or a combination of it is not there in the process. So when we do a study, it provides us the insight to it. Or sometimes, the specification limit itself may be a little unreasonable, either if it is an internal control limit or it could be a customer specification limit, as against the technology we have or the kind of process or the machines we have. So all this put together gives us an insight so that we can have a baseline metric for measurement in the measure phase before we embark on a Lean Six Sigma project, to find out the root cause and then take necessary action to make an improvement. So when we make an improvement, we measure the quantum of improvement over the initial measurement, which is called as the baseline. Now let me give a real world example. Take the case of Blinkit, the groceries delivery to a home. Let us say that they commit to give the delivery within 10 minutes. Now look at a possibility where the delivery boy is given a bicycle. Now the question is bicycle appropriate to make such a fast delivery in a larger city? The answer is no. So the delivery time variation could be wide if you don't give the appropriate vehicle to the delivery boy. So the question is, that is variation. Second is, the delivery boy also may start a little late with the collection of groceries. So he is always off center. He might be a lazy guy. He must be taking a coffee or tea and then taking it easy and then starting. So due to traffic conditions and other things, he may always overshoot the 10-minute spread, what is given to him due to a late start. So these are some of the examples in the real world where these things occur. And some other examples could be what you call as H signs. Whenever you see these signs in business, you can be rest assured that your process needs a capability check. It could be high defect rates, which is your measurement of DPU or DPMO. We will do some calculations a little later. It could be rework resulting in loss of time and manpower. It could be customer complaints whenever he measures and finds that your product is not up to the mark. It is your own difficulty in the process or in the skill level to meet the specification. It could be a scrap where you lose money in terms of wastage of time and material. It could be the long cycle times, as we saw in the case of patients waiting in a hospital. It could be an inconsistent output resulting in wide variation in an unpredictable measurement. And sometimes it's a regulatory non-compliance, which means as per the law or as per the legal requirements. Let us say, for instance, your pollution. Your automobile has to emit out smoke pollution levels within a particular limit. So if your motor car emits a higher level of pollution, then it is measured and you are subject to a penalty. So these are some of the issues where you can be rest assured that you need a capability check. Now, what does the capability check establish? The check establishes three scenarios. One is your Six Sigma, that is the allowed process spread, is less than the specification limit, upper specification minus lower specification, which means the process is capable. The second scenario is your process is capable, reliable, and it does not produce defects. Then the DPMO or the DPU is very less. Now, the second scenario is your Six Sigma is just about equal to the specification limit. In this case, it is a just marginally capable process where you run the risk of the process getting shifted, that is away from the center. Like I gave you the example of a pilot landing. And this could also result in certain probability of risk associated that you may not meet the specifications. The third situation is where your process is not capable, where the Six Sigma limits or the process variation far exceeds the specification limits, and you call it as incapable process. Now, how to measure this? There are some indices to measure this over the short term and over the long term. So why do we need to understand both the short term and the long term? So short term, particularly in a service industry or in a manufacturing industry, let us say you do it for smaller number of batches or fewer number of runs during a lesser period. The process is likely to show that it is capable, because in the short term, everybody will be consistent, be it a pizza delivery boy, a new boy who has joined his profession, or it could be a new aircraft, or it could be a new machine. But over a long term, what happens is over multiple batches or the multiple runs, the process gets shifted. That is where you talk of a process shift of 1.5 sigma, which is allowed in the DPMO calculations, which you have already studied in the previous session. So how do you collect data for a capability study over the short term? There is a narrow inference space, say a daily or weekly or a shift or a particular machine or operator. And there are only common causes. We also studied what is a common cause and what is a special cause. So in the short run, there are no special causes. There are no assignable causes. And normally people or the machine works at a optimal performance level. And typically the sample size is 30 to 50. Now, the long term can be slightly over a longer period, a monthly or a quarterly, against a wider cross section, that is the sampling, stratified sampling, if I may say, multiple shifts, machines and operators. And here in a long-term study, you have both the common causes and the special causes, so that your calculations can take care of the assignable causes as well. And whatever results you get out of the capability check is far more closer to reality, because all these errors are factored into the sampling study. And here you take about 100 to 200 data points. So if you look at this picture for a particular process or the short term, you have fairly things fairly under control, but over the longer term, the pattern of the curve is slightly different, and you can do. But maybe I'll show you the next slide, which will be make it more easier for you to understand. So for example, here, take this example. Shorter term, the mean is not shifted. Okay, the mean is shifted for different samples, but you can see that over a longer term, there is a visible improvement here, or some causes are removed, although the runs look similar. If you plot the variation, if you see the pattern of the curve, they look similar for a particular run. But if you aggregate the measurements, it looks something like this, where the variation is always within the 3 sigma limits in the shorter run. And there could be certain batches where the center could be shifted one side of the specification, either on the left side or on the right side. But over the longer term, all this is addressed in terms of the both the centering as well as in the off target, and you have a fairly consistent measurement, which is a normal curve which is centered around the mean. So the short-term capabilities have a notation called CP, and the long-term notation has got a notation called PP. Now, with all this understanding so far, how to measure the baseline? So the baseline is, it is preferable to take a long-term baseline. So what is the definition of a baseline? The average long-term performance level of a process when all input variables are unconstrained. That is, they should not be constrained in terms of certain input parameters. And that is how you can see that the fourth measurement is fairly, the process is centered around the mean and also not off the target. And this calculation, you can take it as a baseline performance. So what you do in a manufacturing industry or a service industry is you compute the short-term capability to establish roughly your control limits. And based on this computation, you fix the control limits for the longer term and see that your process is first stable. That is, stability means the special causes are removed, and then you make the measurements for process capability, so that you get a fairly representative baseline performance of the current process. Any questions here for those people who are in the real-time experience? You might understand that the first step would be to establish the control limits with a short-run study, and then later on use the control limits to ensure that the process is stable, and then go on to calculate the capability indices for the revised control limits. Clear? So we will see it with more examples as we go along ahead when we do the control charts. So the short-term process capability is a hope that the long-term capability needs of the customer will be met. So it's a possibility that the process is perfectly centered, but there's an uncertainty associated with it. So we call that as a process potential. CP is called as a process potential. But whereas the reality is the measurement over the long term, which is called PPK, and this is how the process is actually running, which gives a fair estimate of your capability to meet the customer requirements relative to the specification limits. Now, just to put it in a matrix, the short-term performance is called CPK and CP. When it considers the centering, it's called CPK. There is a different index. We'll see how to calculate that. When you don't consider the centering, then it is called the inherent capability, which is called CP. Similar indices over the long term, you call it as PPK and PP. Remember these terminologies, and remember the terminologies associated with short term, long term, against centering and not centering. We will see some examples and which will make it more clearer. So that brings us to two formulae for the short term and the long term. The short term is for the 3 sigma limits, which is always from one side, that is the closest specification. Either it could be upper specification limit or the lower specification limit. That is the location of the mean from the either of the specification limits, divided by 3 times the standard deviation. But whereas for the long term, we take 6 standard deviation and calculate this. So let's not get into a very deep statistical treatment of this, but remember that for the short term, these are the standard deviation limits 3s and 6s. While for the longer term, it is the entire specification limit. For the shorter term, it's about one half of it. Now, let me go a little conceptual now. So what should be the value before we get deep dive into the formulas and start calculating through a real world example? So what should be the permissible values of this CP, CPK, PP, PPK and all those things? So let me go back to the fundamentals what we learned in the previous session, and let me talk about a Six Sigma process now. A Six Sigma process is shown in the picture on the left hand side, where the process variation is 6 sigma and we are permitted about 12 sigma, 6 sigma on either side. So what happens here? When you put the formula of the process variation divided by the specification divided by the process variation, then roughly if you want to have a figure of 2, then your process should be 6 sigma and your specification limit should be 12 sigma. Okay, so that doesn't happen in the real world. You don't have the luxury of any process working to such close tolerances, and at the same time you don't have the luxury of the customer giving you such a bandwidth to deliver a service or produce a product. So that brings us to another calculation. I mean, that brings us to a calculation where we also consider this 1.5 sigma shift. So considering that we have the luxury, at the same time there is a 1.5 sigma shift over the long term due to inherent variation in the process. That brings us to about 4.5 sigma. So instead of 6 sigma, if you put the 4.5 sigma in the numerator, we get a value of 1.5. Still, even if your mean is off-centered by 1.5 sigma, still your process is capable, which means a value of CPK 1.5 is still considered to be good. But without the centering, if you are talking of the inherent capability, that is the CP in the first picture, it should be 2. So for an ultimate excellent process capability, you have to aim for CP and CPK both 2, which in reality may not be possible. So you have to have a situation where even a CPK 1.5 or a CP2 or up to 1.5 should be a acceptable, reasonably good process. So is that fundamental clear now? Let me put another picture for you to put a range of values for 3 sigma, 4 sigma and 6 sigma. So if CPK is less than 1, which is not capable, so which means your process runs an inherent risk of producing a large percentage of reject projects as per your DPMO table. If your CPK is between 1 and 1.5, still you run some risk of producing reject products. But at a level of 1.33, you have a 4 sigma value, which means at 4 sigma, you can be rest assured that you have a good CPK value. So don't get too much into calculations. Just remember these figures for the moment. And later on, when you become an expert in calculations, you can calculate and then see whether these values are matching. And if anything above 1.67 is a 5 sigma this thing, which means your process is good. Anything more than 4 sigma is considered to be a good process. And again, as I said in earlier sessions, the values could differ from machine to machine, process to process, industry to industry. So it is your own benchmark of 3 sigma, 4 sigma, but we expect a minimum of 3 sigma, that is 1.33, both for CP and CPK, so that you end up with about 600 or 6,000 defects per million opportunities as per the normal curve and the DPMO table. So let us take a few examples now, just to reinforce this numerical concept in your mind. So CP 1.67 and CPK anything more than 1.67 is capable and centered. If it comes in your calculations, anything less than 1, it shows that either it is too much off-centered. Okay, but CP could be anything more than 1, but CPK, you are only seeing the CPK for the off-centering. CP is the spread. Your spread may be good, but your off-center may be bad. So which means your CPK is less than 1. Similarly, if your CPK is less than 1 and it's not capable, so your CP is also less than 1, then it's not centered as well as it's not capable. So these are certain scenarios where you can remember these values, and you can remember also this table where both CPK and CP and CPK greater than 1.33, it's a highly capable, reliable. You can maintain the process, you can monitor it to see that it doesn't go bad. And if it is between 1 and 1.33, it can be marginal and needs improvement. So you need to reduce the variation and improve it further. And similarly, if it is 1, then you need to really investigate it for the causes and make sure that your process is corrected so that it increases, the value increases. And that is where you do some redesign of the process as well as retraining the staff. It may be a new person who has to be trained to produce a more correct product. It could be a new pizza delivery boy who has to gain some experience in delivery within the time given. So remember these values for you to understand what is acceptable and what is not acceptable. So now let me give you a numerical problem. You have a sample data. You have a process average, that is the mean, and the standard deviation, that is AS. And you have the upper specification limit and the lower specification limit. I'll give you about 3 minutes. You please compute and let us go through the answers together. You can do it in pairs or you can do it within your desk. So if you have completed it, then let us calculate it. CP is equal to tolerance upon 6 sigma, that is the USL minus the LSL, the lower values, and then 6 into the standard deviation given. Pretty much a straightforward calculation. And CPK, the formula is minimum of one side calculation, whether it is USL minus the mean or the mean minus the LSL. So that gives you 2 sets of computation. That is the first one is USL minus the mean. The second one is the LSL minus the mean, divided by 3 sigma limits, as I told you. So the minimum of these values, that is you get 2 results, one is 0.7 and another is 0.64. So eventually you accept the value of 0.64, which is the minimum of these 2 values. And how do you interpret that? Based on what we discussed earlier. What do you think is the inherent capability? Both are less than 1. Both CP, the inherent spread is also less than 1. And similarly, it is off-centered because 0.76 is also less than 1. So ultimately, you have to write as a Lean Six Sigma black belt. You need to write down the interpretation. Since the minimum acceptable value is 1.33 for a value of 3 sigma limits, the value of 0.703 indicates that the process cannot meet the requirements. So either you have to adjust the process closer to the center, but now if you adjust it closer to the center, your CPK value is also less. So adjusting also doesn't help you to achieve an acceptable process. So considering only the inherent variability of the process, that is CP, it does not meet the closer to even 1. So your process can be concluded as definitely incapable, and you can launch your Lean Six Sigma project to identify the root causes and proceed further with the solutions which are possible, to analyze the root cause first, then go to the solutions and then do that in your process. Is it clear now within the Lean Six Sigma DMAC framework? Now I'll give you another example, which is more of a conceptual understanding to see whether you have understood how to interpret the result. So let me give you a set of values of CP and CPK, and let me ask you how do you see the variation, the shift, and or the both? How do you interpret the result? If I give you numerical problems and you get these values as results. Think over in pairs and let me have one answer from each desk. The first situation is CP of 2 and CPK of minus 0.1. What do you think about the spread or the variation or the shift? Variation is a spread, shift, or is it a both? CP is a good value, 2, 6 sigma. Minus 1.1 is a very less value. So what do you say? The variation, similarly, go to the next scenarios, 0.7, again minus value, is less than 1 here. And here again it's 2. CPK has a good value here, more than 1.33, almost closer to 1.5 sigma limits. And in the last scenario, both are less, like the numerical problem we saw later. So how do you arrive at the interpretation? So let us go quickly through this. In the first case, variation is low, which means CP is high. It is good. Variation is low. Shift is high. In the second case, variation is high because it's less than 1. CP is less than 1. Shift is also high. It is also less than 1 with a minus sign. Take the third one. Again, similar to the first one, where the inherent capability is good, low variation. Spread is less, but the shift is also good, which means there is a low shift. In other words, the scenario 3 is the best acceptable process. Low variation, low shift. Take the fourth one, where both are less than 1, which means the spread is high, the inherent capability, the spread is high, and also the shift. There is no shift here. So in other words, there is no point in accepting a process where the spread is high, but the shift is within the mean. So ultimately, it is the CP value which is more important than the CPK when you get a situation like this. So is it clear now how to interpret the result based on the computations in the numerical problems you get? Any questions on this? Practice a few more numerical examples which I give you as homework, and you will be very clear on how to interpret the result as a black belt and guide the projects for further steps. Let me give you now a brain teaser, which you can do it in a group and think over, and then one person from each group can answer this question. So there are two Singh brothers hailing from Punjab. I hope there are no Sardajis in this class. No, what you call, no insult intended. There is nothing such here. So take it easy. They want to participate. They are very good sportsmen. They want to participate in the Olympic selection process. One gentleman has a local gun, which is a Desi gun made in Punjab. The other gun has got an imported gun. Both of them are given a certain number of bullets and asked to fire to get selected in the Olympics. So one of the guys fires the bullets in such a way that all are outside the target. The second guy has 50% in the target and 50% near to the target. So just try to draw a shooting board with circles, concentric circles, and then try to picture this Santa Singh and Banta Singh, the way they shoot. And then you start discussing amongst yourselves. So given a choice out of the two shooters, if I say only one shooter has to be selected for the Olympics, which shooter would it be? Think over and let me know the answer. 2 minutes, we will take about 2 to 3 minutes, and then you can prepare your answer and then answer one from each desk. So let me go through the solution now. So let me go to the previous table. Now, just this previous table is just to reinforce the theory to you, reinforce the understanding so far to you, so that you can look at this problem in a better way. That's the reason why I've reproduced this table. But let me put the picture which I asked you to draw. Is this correct for Santa Singh? That is, most of the bullets are off the target, the bullseye at the center, but fairly close to each other, which means it's off center, but the spread is very less. Here you call it as somewhat like a precision. Then go to the other guy, Banta Singh. If I may draw a picture, 50% of the bullets are at the bullseye, the center, and the 50% of the bullets are spread all over, which means here the variation is higher, the spread is higher. So which guy would you select for selection in the Olympics? Is a guy who shoots 100 bullets off center is a better guy, or is a shooter who gets 50% right and 50% with a wide variation, that is the CP, is a better shooter? It's a very interesting and tricky question. So now if you map these two things to the above table, so may I say that Santa Singh, the variation is low, the shift is high, with a kind of scenario we saw in the previous example. Now, which scenario do you think Banta Singh is? 2, 3, 4 out of 2, 3, 4. This guy has got a high variation, which means you go to straight away scenario 4, but no shift. So which one do you prefer? Who is more likely to do better in the Olympics? And what is the expectation there? So the answer to that question is the inherent capability of Santa Singh, the first guy, is good because he is able to shoot all the 100 bullets fairly close to each other. CPK may be low, but CP is high. CPK also can be negative, that's okay. But Santa Singh has got a better chance of winning the Olympics. Why? Because this guy has got some sense of shift. Either he is aiming a little further down, or he is positioning his gun. In Olympics, the gun is positioned on a stand. If you are able to shift the gun's position, then this fellow's problem of off-centering can be easily solved. But the first guy inherently seems to have a lesser skill. The second guy seems to have a lesser skill. So the answer is I would prefer Santa Singh as a better choice with some process adjustments in the gun or in the way he keeps the gun or finding out the real cause for it. He could be a better bet to win at the selection for the Olympics. Is that clear, gentlemen? Was it interesting? Thank you so much for your participation. So far we talked about process capability, continuous data, that is the variable data. Now let me quickly throw some light on the service industry, which normally uses the attribute data without measurements. So in the case of attribute data, we have studied the normal curve where you calculate the Z value, which is given by X minus X bar by standard deviation. So if you look at the CPK and the PPK formula, it is similar to that. Closest specification minus X bar by 3S. The variables are the same. So an attribute data, you can do the computation in a slightly different way and then still calculate the process capability. So what happens in an attribute data is you get the count of defects, which is called defects per unit, which we have seen in the earlier cases where you note the errors in an invoice or the mistakes you make in a product. So all this is available to you. The data is available to you, defects per unit and defects per million opportunities. So when you map this attribute data, which is available to you, you can always get the Z value. Let us see how to do it. Let us take an example and straight away make it easier for you to understand. A customer service group is interested in estimating the capability of their call center. There are 20,000 calls coming in during a month, out of which 2,666 calls are dropped. So the sample size is 20,000, the defects are 2,000. So you can calculate the DPU, or if necessary, you can calculate the DPMO also, and then you can calculate the capability. What are the steps to solve here? First one is calculate DPU if the data is available, or if you want to calculate DPMO, that's also possible. Look at the value of DPU or the DPMO in an appropriate table to get the Z value. Once you get the Z score, put that in the equation and convert the Z score into a CPK or PPK where the formulas are similar. So for those of you who have a little bit of mathematics, this is easy, but don't get worried. Mathematics is not a difficult subject. It's a pretty much common sense. So let us do the calculation here. So DPU is 2666 divided by 20,000 given in the sample size of 0.133 defects per unit. You are done with the first step. Go to the second step. The table is provided to you. So let us look at this table now, which I have not introduced to you so far. So the Z in the short term and the Z in the long term, you have to do some manipulations similar to the concept we studied, that capability in the short term and the capability in the long term. So the Z value, you subtract 1.5 from the long term, and for long term, you add 1.5. Okay, if you are asked to convert it, but normally this may not be necessary in a straight calculation. So that is how this shift of short term and long term capability is accounted in an attribute computation. So attribute data is always long term. Remember that attribute data is always long term because it's easier to count and it requires so many samples to get a good estimate. So remember that whenever example is given from service industry or an attribute data, remember to use only the long term. That is subtract, add 1.5. Okay. So go to the Z table, which is provided to you, and look at this value here. You get a computed value in the previous DPU, that is 0.133. So look for that value in the table and draw two lines, one horizontal and the one vertical, to get the Z value. So don't worry how this is got. This is all ready-made tables given to you. If you are using a software, there's no need to rackle your brain at all. So 1.1, go to one more decimal. So decimal is 1.11. So for a corresponding value of DPU 0.13350, you have a Z long term of 1.11. So if you were to convert it into the short term, ZLT to ZST, then you have to subtract ZST, I think ZLT to ZST. So add 1.5, ZLT to ZST. So 1.11 plus 1.5, 2.61. So you are getting a value of Z to 2.61. So you are pretty much done with the third step, that is the Z score. Now the last step is convert the Z score into CPK and PPK. Very simple. Step 3, short term 3 sigma, ZCT, that is CPK divided by PPK, both are short term. This is a long term. So if you are using the Z values for the long term, use a manipulated term with addition. You get 1.11 divided by 3. And Z for the short term, this is a manipulated term. This is, you have added 1.5 here. So 2.61 by 3 for the long term, it's 1.113, and use a proper notation, which we learned earlier, and you get 0.37 and 0.54. So you can see that the longer term value has got a lesser value, which is a fair this thing for attribute data. So you can consider 0.37 as a fair representation of the attribute data. This is an index of how close it measures to the specification limits, indicating the natural variability of a process. So is a process capable? Go back to your understanding of whether it is less than 1. So it is less than 1. It is too much off center. Definitely it's not capable. We have not calculated CP here. Don't worry about it. This is just an example of how to do it for attribute data. Now in a software, you don't have to do anything. You just have to input the values and it gives you. So now that pretty much completes the session on the fundamentals of the process capability. Now, as I said earlier, you may not be a mathematical expert, but still, when you have a software and when you have Microsoft Excel, even it's a child's play. So normally the practitioners use Microsoft Excel or Minitab. But if you are a green belt or a black belt, you should understand what the Excel sheet or what the Minitab does it for you. So let us look at the Microsoft Excel. The templates are available in the public domain, wherein you can just input an attribute data or a variable data. And then all the formulas are defined for you to get CP, CPK, CP, all that, all the 4, this thing including. So either you can input the defects or you can input the USL and the LSL, and certain fields are blocked, and depending on whatever you need, you get the remaining calculation. It's pretty much a simple Excel with formulas defined. If you are good in Excel, you can go ahead and define these formulas yourself and see whether this works for you. Otherwise, use a template which is given to you. Or for those of the companies who have a mini tab, it's a menu driven software where the data has to be entered in the spreadsheet. It's pretty much similar to Excel. Go to the menu and pick up the menu of process capability studies and make some judgments, make some assumptions there. And that will come through the help. You can learn it through the help facility there. And out you press the button, you get the answer with quite some tables nearby and the histogram where it is superimposed by a normal curve. And how to interpret these results? You have the values of PP, PPK, CP, and all that here. In addition to that, there's a lot of other things which you can do. All this is given to you, and the software is pretty much user friendly. You can learn it through examples given and through the help. And for both the green belt exam and the black belt exam, you don't have to use either an Excel or you don't have to use either a Minitab. You got to just learn to do the calculation so that you can pick up the right choice in a multiple choice situation. Now, to end the session for all those practitioners, it's not just the theory, but when you are a Lean Six Sigma practitioner, you get into several learning situations. So the common pitfalls are don't calculate on an unstable process. What is an unstable process? Where the assignable causes are there and special causes are there and you don't get correct results. So the first thing would be remove the special causes, make sure the process is stable, draw a control chart, and then calculate CP/CP. This is what I said when I talked about the short run and the long-term run, where you, the short term, you collect data, establish the control limits, make sure that the process is stable, and then go for a capability study. So always check process stability first using control charts after the short-term study. Control charts are your own limits. Statistical control is not capability. When we study control charts, you will understand that control charts are not capability studies. But however, they can be used as well. Continually validated with new data. Now, capability is something which is unpredictable. So you got to, it's a dynamic process where you got to keep studying this on a continuous basis. So that brings us to the end of this session on capability, process capability. What we learned was it's a statistical measure to measure the inherent capability of a process, which is CP, and off-centering and variation. Capability analysis provides quantitative assessments, both in terms of variation and off-centering. You have two ratios, but the CP is the ratio of the specification spread to the process spread. And normally you can accept a shift of 1.5 times the long-term run. So you effectively are calculating it not for 6 sigma, but 4.5 sigma. And the process mean shifts a little bit over the long term, which is due to inherent variations in any process. And capability indices serves as a health check for process consistency within specs so that you don't run the risk of not meeting customer specifications in delivering a product or in making a product. And you don't have the risk of producing defects, rework, and such on. Hope the concepts are clear. I'm giving you some problems as homework. We will revisit those problems next time for a reinforcement of what you have understood in this session. And that is pretty much the end of what value I have to give you. Thank you so much for this session and wish you all the best.